For this video, I'll be working through question 3 of the 2018 Scholarship Physics exam. Question 3. Right, we see that. Show that the force of the gravitational attraction between a pair of electrons is about 10 to the negative 43 times the force of the electrostatic repulsion. This is the electrostatic repulsion equation where K is Coulomb is constant, Q is a charge of an electron, and R is a separation between the two. All in all, this question's like a higgledy-piggledy question. It's got sort of questions on every sort of area of the whole, of all of year 13 and 12 physics. This is a pretty common sort of, common knowledge sort of thing. Like gravity is very, very weak compared to the nuclear strong and the electromagnetic force. So basically what you want to do is have a ratio of the force of gravity, and because this is a times 10 to the negative 43, it means it's going to be divided by, what is it, what do I call it, FQ? FK. What do I call it, FQ? Right, so it's basically saying is the force, the electrostatic force between two electrons is this denominator is huge compared to the numerator. Anyway, so we'll put the two equations. So I'm going to just do like a little bit of year 10 math. Gm, because there's not much space, little m over r squared, because that's the separation distance between the two, divided by, I'm going to use the old school year 10 divided by k, q1, q2. Those are just charges on the electrons. Two identical electrons, so really I could just have q squared, but I'll get to this soon. And then r squared again, because that is up there. So this is the gravitational formula. It's in your formula sheet, although you would have memorized it by now. Rightio. And that is the same as if you get a fraction divided by another fraction, you flip that fraction and make it multiplication. So that's what I'm going to do. We go g, big M, little m over r squared times r squared over, what do we got, k, and screw it, I want to make it q squared, because the charges are identical. There's two perfectly identical electrons, and that is going to give me, I'll cancel my r's out, can we see that? And the mass is identical as well. It's two identical electrons. We're going to have g, I'll just go little m, because little m is kind of cuter, and electrons are tiny, over k, q squared. Sweet as. And what we'll do is, this is a show question, so you need to show algebraically, and then you need to substitute in your numbers, which is going to be, what is it, 6.67 times 10 to the negative 11 times, was it 9.11 times 10 to the negative 32, I'm going to put some brackets around this number, squared, divided by 8.8, oh crap, that's 98, oops, God, messy, huh? Times 10 to the 9, because it is Coulomb's constant, times charge on electron, which is 1.6, well, it should be negative, but it squares it out, it squares it, so it makes it positive, times 10 to the negative, what is it, 19, that's a charge on electron, and I'll put brackets around this, and I'll square that, and that equals 2.4 times 10 to the negative 43, which is pretty much 10 to the 43. Oh, God, 10 to the power of negative 43. Did I write that correctly? Yes, I did. There we go. So it showed that it's dramatically, the force of gravity is dramatically less than the, it's certainly not a one-to-one, that's for sure. Right, so an experimenter is given a black box with two electrical terminals. The experimenter knows inside the box are exactly one inductor, one capacitor, and one resistor, but does not know the combination of parallel and series connections inside the box. Using an AC generator with variable frequency and fixed voltage, the experimenter measures the magnitude of the AC current as a function of frequency and obtains the following graph. So as we can see, it's been capped out. I assume if I had a ruler, I do have a ruler, but that's close enough. I mean, it has a max current, which implies there's a series resistor. Also, so this is something new. This is not a unique way to do circuits, but if you ever go to university, the way you do circuits is kind of a bit different to this. So this is something new that I've come across, although I'm familiar with it in a different context. This is what's called a tank circuit for a Tesla coil. So I'll do the opposite. If you flip this around, we have a max current when there's a frequency of some special frequency, and this would probably definitely be familiar to you, I should say. This is a resonant LCR circuit where you have a capacitor and an inductor at resonance. Because they're at resonance, the total reactance cancels out, so you get no reactance whatsoever, and you get maximum current. And so that's. But if you flip this around, you have essentially here you've got a point where there's infinite resistance or reactance, or infinite impedance. You know that for sure. Likely it's not the resistor doing anything, because the resistor's over here doing nothing. So it is infinite reactance, and that only can occur when you have a capacitor and inductor in parallel at resonance. So I'll pause, write out a quick answer, and then we'll discuss why. Right, so I've said a resistor is in series with a capacitor and an inductor in parallel together. And I've sketched it up as well, so like the examiner can see what you were talking about. And then over the page I gave the reason why. So there's a maximum current, so there must be a resistor in series, which is capping the current. At a select frequency, there is no current. To do this, you need infinite reactance, I should say. So an inductor and capacitor in parallel. I haven't found a good explanation to why this works. All the explanations I have sort of loopholes. I know it's called a tank circuit. I know how they work. I know that they do work. You can have other variants of these circuits where it's an oscillator circuit and just remember these are ideal components. So on a computer they work. In reality, you still might get a little bit of current because you'll have parasitic draw and stuff like that. Oh, maybe not. You can have just these two together, and if these are perfectly ideal, they'll oscillate forever at a select frequency. That's an oscillator circuit. But yeah, enough of that. I'll post in the description the physics stack exchange answer, which is a lot more comprehensive than what I can cover in this video. Right. A resistance of 4 ohms is connected across a cell of internal resistance R. As shown below, the 4 ohm resistor dissipates energy at 16 watts. The 4 ohm resistor is replaced with a 1 ohm resistor, which also dissipates energy at 16 watts. Show that the source voltage must be 12 volts. Right, so I assume there's a few ways to do this. The way the answer schedule does this is quite eloquent, and that's the way I initially went about doing things. First, when you do this, you've got power is equal to IV, which is equal to I squared R. This is the typical form. You can also have V squared over R as well, but it's a little less typical. So what you're going to do is you're going to write down like some things that you know for sure. So your initial current, I initial, it's just the voltage, and this is, I'll just write in the circuit here, the voltage you get is equal to the EMF minus, this is like the sticker voltage of the battery. I always just say it's a sticker voltage, but it's the maximum voltage you get with no current flowing, minus the parasitic voltage that's dropping across that itty bitty resistor, right? Divided by voltage divided by resistance. So in this case, it's the internal resistance plus 4 ohms, and we know the final current is equal to the same voltage divided by, what do we got? R plus 1. So this is total voltage across. Ooh, hold up. I have made a notation error. Technically speaking, this is the EMF, because this is the total voltage of the circuit divided by the total current of the circuit. Just keep that in mind, but I'm gonna leave it just how it is. Power is equal to I squared R, which in this case we are going to substitute. We know this is equal to 16, but we're going to substitute these fellas into here and just see what happens. So we're going to have, what do we have? We got V. Ooh, hold up. Equals V squared over R. I know what I've done. So we need to square this, so it's going to be v squared over r plus 4 squared, because it's I squared, so this whole thing is squared, times the resistance. In this case, the resistance is 4 for this time, I'll check it times 4, for the initial current. This is the initial current, and then that's equal to, the power is the same for the final current formula, so I'm going to go v squared, because I'm going to square this whole thing, because that is I, v squared over r plus 1 squared times 1. I've chucked the times 1 in there just so I know what I'm doing, and this is all equal to 16. This is all equal to 16. So what I'm going to do is I'm going to shuffle some things. I'm going to move this up, move that across to the side, possibly cancel some things out, and then find either R or V. It looks like, just looking at it now, I'm going to end up finding R, because R will end up being like a quadratic. The V's, I can see they're going to cancel out. If I find R, I can substitute R into here. No, wait, I can substitute into here and find what V is, because I know power is equal to 16. Easy. Right, so I'm going to have 4V squared bracket R plus 2, plus 1 bracket squared is equal to 1 times V squared R plus 4 bracket squared. As you can see, yeah, the V's are going to cancel out. You just divide both sides by V, and then I'm going to blow these brackets up, so I'm going to get 4R squared, I hope I can see that, plus 8R plus 14 minus R squared plus 8, minus 8R minus, have I done that right? Yeah, I hope so. Minus 16. I hope I've done that right. Sweet. And that is all equal to 0. And that should cancel out. What do we get? 4, 2. That sounded a bit fishy. This is 4, not 14. Of course it's 4, because it's 1 squared times 4. There we go. That makes more sense. So I should get 3R squared. 3R squared. The 8's cancel out. Positive 8 minus 8, that cancels out. And then I have plus 4 minus 16. That leaves me minus 12. So that should be equal to 12. In other words, you can see pretty quickly that R is equal to 2. So the internal resistance is equal to 2 ohms. Just because you can divide both sides by 3 gives you R squared equals 4, R equals 2, or positive or negative 2, but there's no such thing as well, let's not talk about negative resistances. Are there such things as negative resistances? I think there are, actually. Anyway, forget about that. Can't be. V squared equals to 16 times, and I know little r is 2 plus 1. I'm just chucking it into this one here. No, this one here. And that equals, that's squared as well. That's why that is squared. No, that's not squared. And that equals 144. Thus, V is equal to square root of 144. I've run out of space, which is equal to 12 volts. I hope that proves it. Yes, it does, because we're looking for 12. Cool. These questions are here just heavy on the algebra. I did this twice. Like when you do your exam, you have like, I haven't printed them out, but you have like a whole, 8 blank pages at the back. Use those pages to do a little bit of algebra, just to write down like roughly what you need. There are other ways to do this question, but I like doing things all algebraically. Right. Explain in detail the key underlying principles of the emission spectra of hydrogen atom. Full stop. So I want to pause, write it, and then discuss. Right, so it said electrons in a hydrogen atom can only have certain energies. This quantization means when an electron transitions from a high energy state to a low energy state, a quantized amount of energy is released in the form of a photon. The energy released determines the frequency of the light, so the large transitions give high frequency, low wavelength light. Quantized just means like, how do I describe it? It's like chunks. Take, for example, integer numbers. Integer numbers are the 1, 2, 3, 4, 5, 6, so on and so forth. They can't include like 1.2, 1.3. Integer numbers are only the whole numbers. Integer numbers are thus quantized. They discrete. There's no in between. There's no half jump or jump and a quarter, and that applies to electrons in really any atom. But in this case, in a hydrogen atom, they can only occupy certain energy states, I suppose. So when they transition up or down from those energy states in the shells, if that's what we're going to call them, a quantized amount of light is released in the form of a photon. I should have mentioned that all the jumps are all identical. There's only a certain amount of different jumps that you can do in an atom, and it'll all give off identical light. But there's not much space. Anyway, that's it.